we start with the limit and then explain the meaning of continuous motion in mathematical terms. Now we learn average velocity, right? And instantaneous velocity is what we're about to enter, and that's kind of explained when h is approaching 0. If you look at the very formula, it is an indeterminate form. But after you calculate it a bit, h is canceled and becomes determinate form. We can calculate the limit, and that limit is instantaneous velocity. Good? And I hope this video works. And oh, it works right away. So this is the motion that is actually happening on this wall. The dot is actually moving up and down. That's the actual motion. And this is space-time. This horizontal axis is a time axis, and vertical axis there is actual location. So if you plot this one, it looks like this, right? And pay attention to how this one's moving, about to move very slow and move forward like that, right? That's the motion, and that happens right here. So if you, for example, if you zoom into this part, let me grab this space-time motion into that and explain this motion a little bit in detail. At that time, around 4.7 seconds, around these in seconds, if you zoom into this part, is nearly like flat line, right? Flat line means here and there, its location, vertical location is not changing. If you look at it here, same amount is just like steep line. So, and given same amount of time, its vertical location is changing quickly. So if you're looking at something like this in the space-time, you know it's moving slowly, right? If you're looking at something like this, very steep, if you just simplify it into a straight line, that means it's moving really fast. And if it is curved around like this, that means it's changing a direction and things like that. So this graph in the space-time can be translated roughly and qualitatively into the motion here like that. Does that make sense? Yeah. From the left to right, it was rising. Left to right, it was pointing it down. It was going down, moving slow, things like that. Those are the space-time. So how much is steep in here? And that kind of correspond to the instantaneous velocity. Save that. Okay. Right. We're going to interpret this one in the space-time graph that naturally allows you to enter the geometry. Before, it was like the red dot, it was on there up and down. We're interpreting everything physically, right? There's actual motion in the space and the time and things like that. But as soon as you enter the space-time, which is everything is interpreted in terms of things in the space-time in this course, so you have to understand that. And once you enter that xy plane, which is really time axis and vertical axis, becomes a geometric object. So geometric interpretation of average velocity, it says, is the slope of a secant line. So I'm going to explain that. For example, if this was t1, that's the time, t equals t1. If that was t2, this time period, and this y2 and y1 are the vertical locations. y2 is here, the y coordinate here is y2, their y coordinate is y1. It's a coordinate relative to y equals 0 in here. At t equals 1, it was in location y1. At t equals t2, a little bit later, that is over there in y2. What is the average velocity? That is precisely the average velocity, right? If we label all those four quantities like that. Make sense? But if you enter the space-time, where horizontal axis is time and vertical axis is space, now what does this mean? Is a slope of some line, right? Slope of what line? Slope of line that connects these two things there. It's actual straight line in this black color, but you can see there's a little bulged up a little bit that, so the blue curve is not really the straight line, but it's almost the same, right? Yeah. So this quantity that we just calculated correspond to slope of what line? the line that cuts through these two measurement points. They call, in that XY coordinate system, they call the secant line. Okay? Make sense? That's the name. So the average velocity is the secant line there, those 2 points. The slope of that line is the average velocity. That's the thing that you have to remember. So here's a various picture. I have these 2 points there. I'm not going to change this left endpoint. I'm going to only change that one. If it is space-time, the distance between these 2 points represent time interval, correct? And this one is where c is, and this is going to be c plus h. Distance between these two things is going to be h. Okay, and that slope of this line is this represented here, and physically that's the average velocity. Good. And if this is, just let me write that down there. That's just an example. The same formula is now have a different interpretation in geometry, and they introduce same formula, but in different contexts. So we're going to call that one slope of a secant line, right there. If you have a function y equals f of x, not really interpreting this time and this vertical axis. Once you enter that, it's just to mathematicians, it's just xy axis. So if you're looking at this graph and you look at these two things, cut through what is the slope of this line, secant line, and m standing for slope, not little m, but just big M, MHC at C here, and that's h, the distance between these 2 points. What is the slope of this line is given by this formula. As you can see, this formula is precisely the same formula you saw in the average velocity, right? Except that f is replaced with, s is replaced with f. Fair enough? So even though I declared this is another formula to remember, but it's kind of the same formula. Next thing I'm doing is that actually see what happens as this h, or the measurement is very, very small, just like these two. So this line is almost the same as that curvy part. And if it is even closer to that, it's represented by blue line. It is this red point is so close to this blue point, so you can't really see it. It is this tiny bit difference, right? Still, you connect those two things, the line looks like this. I hope you see the way this blue line is intersecting this black curve is different from the red line intersecting the black curve, right? So we call it the blue line is just touching that the black curve, and this red line is cutting through those black curve. Is that right? Yeah. When it's in that quality, we call it a tangent line. If it is cutting through 2 points, it's called a secant line, right? By doing that, getting closer and closer, you will never reach to that blue line. You have to make that jump. Okay, that is the limit, right? So that is the ideal position. That jump, if you get to that line, is called a tangent line. Secant line versus a tangent line. That's very subtle, right? Mathematically defining it is easy, right? Using this limit, but explaining is tricky because you will never actually get to that blue line by that process. All right, I think we explained that. I think I'm just summarizing it here. Let me do that in the next page. Just going to copy that down. All right, reviewing instantaneous velocity is given by this formula. Let me change that to S there. I should change my file ST, and that's S there, S and S. Velocity. All right, what's the difference? Instantaneous velocity versus average velocity? You see the similarity, right? But instantaneous velocity has one more thing. What is it? Limit, right. Without a limit, that will be just average velocity. H is however small. Now we're sending that H to 0, and We define that as instantaneous velocity there. All right. And VC is called velocity. At C, what is the instantaneous velocity? Consider average velocity in h equals 0. That gives you the velocity. So time assigned with a velocity, that's a velocity function. And this is every notation is correct. Slope of a tangent line. So here's its slope function. They don't call it a slope function, but I have to give some name to that. Y equals f of x, not necessarily coming from position and time. Just write down y equals whatever the formula, and then you have a curve in there, right? Like that. And you look at the C, and let me use this different point over here. This is where x equals c, and I want to draw a tangent line in there. It's tricky. Tangent line. Let me show you how I actually sketch the tangent line. It's a line that touches this one. So it has to kind of point it like this and point it like that. So if you kind of zoom in there, it always just touches one point, not cutting through this too, right? I often use this. If you have a straight edge on the floor here, the way the coin is touching that straight edge, that's the tangency right there. So that kind of thing is explained here. All right. So there's this straightforward definition of a slope of a tangent line. Write down slope of the secant line and put the limit to it, right? Understanding what exactly this line is in terms of one process at a time, getting to that is tricky. But that's the definition. If you're asked to calculate slope of the tangent line, you're not supposed to go to this graph and speculate. You just cold blood calculation of this limit we have practiced so far. That's what we're supposed to be doing. All right? Instantaneous velocity, slope of the tangent line, same thing in different context. There's one more thing that is coming in, is this one. Mathematicians like to put themselves in a different context, not geometry, not physics, just pure algebra. And for some reason, they name it different. This is analysis. All right? We don't want to look at the function inside xy plane. If you have a function given by sine x, so be it. Sine x is a function, right? Okay, there's no problem with that. We know what the function is. And you don't enter xy coordinate system. You just accept it as a function. I give you sine x and you accept it as a sine x. There's an input and output relation, right? Then we define this new function. You've seen this one over and over, right? It is all motivated from this physics part, but they just want to define in a different context. Not in the geometry, not in the physics, just the function. We're going to consider this limit, f of c plus h minus f of c, 1 divided by h. You're like mathematical slaves. You don't think. I give you just formula and you just calculate it, right? That's what this one is. Don't go to the real world where the geometry, physics, give our existence. And here is just function, and you're asked to do this one, and you ask no question. You just calculate it. That's what this one is. Then name it. What is the name of this thing? Derivative, right? The instantaneous velocity, slope of a tangent line, is now formalized into a pure mathematical world to, what is the name? Derivative. Most important part of understanding the derivative is understanding this as a function. If you have not, I want you to go ahead and box it, put 5 stars and underline it like 50 times. Like that. What is a derivative? Derivative is a function. You have to recognize it. So what is a function? A function is that you give an input, you get an output, right? If you understand the procedure of getting an output from the input, you understood the function. And mathematicians say the function is defined, even though you don't have a formula. All right. For example, I give you 15. And then you go ahead and calculate the 15th prime number. Do you know what a prime number is? Prime number? Yeah. Go ahead and diligently calculate 15th prime number, right? And whatever it is, you get that 15th prime number, right? Good. You understood the instruction, right? I give you an n, and is not specified, and then I ask you to go and find the nth prime number. Then you understood what to do, right? As soon as I give you a number, you'll go and find that number, right? So everybody understand this instruction? Okay, if this instruction is understood, mathematicians say the function is defined. Function is defined in your mind. That's the same thing in here. If I give you a c, what are you going to do with the c? You consider this limit, right? F of c plus h and f of minus. So we understand c, what is h? H is going to disappear as h approaches 0, right? So compute that quantity, and whatever that number is, that's the output. C is the input, and that f, whatever the limit value you get, that's the output. So because you understand how to compute the limit, the concept of a limit, this is understood, right? I give you a number, you calculate right-hand side, whatever that instruction is given to you. Therefore, we say this function is defined for you. Whether you can have a nice formula so that you can calculate it quickly without going through limit h approaches equals 0 is not really part of this function. It's defined, all right? That's a separate question. What is the quick formula for this function? And that's a different one, right? So here's a formula, and I was emphasizing, hope you see this as a function. And what was the key to understand this as a function? I give you an input, and you understand the instruction how to do what to do with that input and getting an output. That's the most general notion of functions, all right? So that's the new function is defined for you. And I hope this makes sense. If function is in mathematics generally defined like this, is the value of a derivative in the context of the physics motion is a velocity in the xy coordinate plane that becomes a slope, right? Okay, so that's the interpretation of a derivative. So this is the meaning of interpretation of derivative. If somebody asks what is a derivative and what is a key word that you should start with? Yeah, it's a function, all right? It's a function. All right.